Everyone. So we continue with our advanced school, and this week we are going to have this contributed talks. And we started today with our first speaker, Makson Santos. He's going to talk about a fully nonlinear free transmission problem. So please, Makson.
Thank you, Juliana. Also, I'd like to thank the organizing committee for the opportunity to give this talk. Today, I'm going to talk about a fully nonlinear free transmission problem that is our work jointly with React. Okay. We studied the fully nonlinear free transmission problem of this form here, where F1 and F2 are lambda elliptic operators, and that means that there exists constants lambda and capital lambda, such that this inequality holds for all m and n in SD. SD is the space of symmetry matrix with n non-negative. Also, Fi is positively homogeneous of degree 1. That is, for every tau in R plus and n in SD, we have this equality. In addition, Fi is a convex operator. Omega plus denotes the positivity set of U, the set where U is positive. And omega minus denotes the negativity set of U, the set where U is negative. Okay, then what you have is this picture, not so good picture, but just to illustrate, this is the simplest case, right? What you have is that in omega plus, we have an equation governed by F1. In omega minus, we have another equation governed by F2. Here we don't have equation, U is 0. But the problem is that we don't know a priori what is the set where U is positive, and we don't know this set. And to know the set, have to go to the function U, but to get information about the solution, we rely on the equation that once again depend on the omega plus and omega minus. This is one of the problems. And also, again, we know what is happening here. We know what is happening here, but we don't know what is happening across this interface. That is the boundary of omega plus union omega minus. We have some applications for this kind of problem. It includes thermal and electromagnetic conductivity, composite materials, and more generally, diffusion processes driven by discontinuous laws. There are some new works related with this theory, and among them we can see the works by Livogelius, Nirenberg, Bao Li, and more recently Caffarelli, Sorriacarro, and Stinger. And these works have one thing in common, that there is the fact that I know a priori the interface, right? The interface is a fixed set that I know a priori, but when I drop this condition, we have what we call the free transmission problems, as they works by Amaro and Teixeira, and more recently Shiravstana. Our results of fully nonlinear transmission problems includes quadratic growth, regularity of the solutions, and classification of the global solutions, right? Okay, when I said before, one of the difficulties is that we don't know a priori the set omega plus and omega minus. But another difficulty is that I don't have an equation in the whole domain, right? I have an equation here and I have an equation here. And because of that, the PDE actually doesn't give us that much information. And what we do then is look for something else that can give us the information that we need. And to do that, we started by noticing that since U is a strong solution to this equation, what we have actually is that this equality is satisfied almost everywhere in omega plus union omega minus, okay? And then it follows that the minimum between F1 and F2 of the ratio of U is less than or equal to 1, and the maximum between F1 and F2 of the ratio of U is greater than or equal to minus 1 almost everywhere in omega plus union omega minus. And in the set where U is 0, this is 0, this is 0, and we're in business, right? Then what we have actually is that U solves two inequalities in the strong sense. Okay? And because of this, we have some consequence. The first one is that by the bonus maximum principle, as stated by Pellions and used by Caffarelli, Crandall, Kotzen, and VH, we have that U is actually continuous and solves this equation here. Now in the whole B1, in the whole set, and in the viscosity sense, okay? And it follows that U belongs to this class of solutions, again, in the whole domain. And because of that, much more is known for this class of solutions. In particular, we have that U is locally here the continuous with universal estimates. Okay. Okay. Now we are ready to prove our first result. That is the quadratic growth, and it's done in 3 steps. The first one, we let x star in B1 be fixed, and consider the maximal subset n whose element j are such that this supremo here is greater or equal than this supremo. Notice that this is a subset of this set here, and we denote such set by m, by this. Okay. Then what you do is first we prove the quadratic growth in this set, right? For j here. Then we can extend this to n, and then we can prove the continuous case. And also, to prove the quadratic growth of the solutions, we consider this quantity here. That is the density of the negative part of U. Okay. Then have this proposition. Let U be a solution to our equation. Suppose that Fi is lambda elliptic, convex, and homogeneous of degree 1. Let x star here in the interface, and suppose that for every j here in the set, we have that V is bounded by above by C0. We call that V is the density of the negative part. Right? Then, if you have this, we can control the growth of U in these balls by this. For every j in M. Yeah. Okay, this is a picture just to illustrate the hypothesis on V, density of the negative set. You can see that in this picture here, when I go from R1 to R2, V is decreasing even faster. And this is a case of our theorem. This is in the scope of our hypothesis. But on the other hand, if you look at this picture here, when I go from R1 to R2, the volume is constant, and it may fail the hypothesis. Then this is the kind of this is the geometry of the free boundary that you are looking at. But this is not the case. Okay, and to prove the quadratic growth, we agree by contradiction. We suppose not. We suppose is false. Then there exist sequences UN and JN such that UN is a normalized strong solution to this equation, to our equation with UN. I have this condition on V is less than 1 over n, but this supremum is greater than this, right? For every Gn n. Here I'm taking x star equal to 0, let's say, without loss of generality. Okay, but now this is bounded, right? It implies that Jn has to go to infinity as n goes to infinity, right? Because of this inequality. Okay, what we do now is we introduce this function Vn, and we notice that it satisfies some properties. The first one is that Vn of 0 is 0. Recall that 0 belongs to the interface, right? Then this is 0, then Vn is 0. Using the definition, we can say that V1 of Vn goes to 0 as n goes to infinity. And this the supremum of V in V1 half is equal to 1. Just look at the definition of V. And the supremum of Vn in V1 is less than 16. Okay. And using these properties and the definition of Vn, we can conclude that Vn satisfies these two inequalities, right? With for some C0, non-negative. And okay, and as before, I'm sorry. I'm in the. Okay, as before, like this, it follows that Vn belongs to this class, and as I mentioned, when I have solutions in this class, I know that they are Hilde continuous locally for some exponent alpha with uniform estimates. It implies by Ascoli-Azela that there exists a V infinity such that Vn converges to V infinity in C beta locally for every beta between 0 and alpha. Okay. Okay, now by using the properties for Vn, we have that V infinity of 0 is 0, and V infinity and the L infinity norm of V infinity is 1, is equal to 1 in V1 half. And because of, and recall that this goes to 0. Okay, this is the density of the negative part of Vn. It goes to 0. Then we can conclude that V infinity is non-negative, in fact. Now, by stability, we can see that V infinity, so with this equation, this is this inequality, okay? And then V infinity belongs to this class of solutions, okay? And attains a minimum interior in 0, okay, at 0. And for this class of solutions, we can use the maximum principle to get a contradiction with this fact, right? And that's it. And then what you do? Okay, we proved the theorem for every j in M in that class. Then what you do, as I said, is now we extend this result to n, to the naturals, and then we can prove the continuous case. Okay. Okay, and now by using the quadratic growth, we can prove the regularity of the solutions. Okay. Have again solution to this to our equation, FI elliptic, convex, and homogeneous of degree 1. We suppose that we can control the density of the negative set by 0 for every x in the interface and intersection b1/2 with some C0 universal. And then we have that U is C11 locally in B1, and there exists a universal constant C0 such that the L infinity norm of the Hessian in B1/2 is bounded by C. Okay. Then what we did was, okay, we started with this, okay, with U satisfying this equation. It says basically that U satisfies an equation here, and U satisfies another equation here. Then we proved that we showed that actually U satisfies two inequalities, but now in the whole domain and in the viscosity sense, okay. And because of that, we could prove the quadratic growth and the regularity of the solutions. And now that we have this, we can do a little better. We can say indeed that U satisfies a uniform elliptic equation in the whole B1, okay, and with G in L infinity. That is better than two inequalities. To see that, it's quite simple. Actually, once I have the regularity, okay, we have that FU1 of the Hessian of U in a point X is 1, almost every X here, in the set where U is positive, 0 in the set of U is 0, and in the set of U is negative, this is this, right? But recall that FU1 is uniformly elliptic, then it implies that this is Lipschitz, okay? And now that I know that U is C11, I know that this is bounded, okay? It means that this whole quantity here is bounded. Hence, we can define G, the operator, equal to FU1, and the function G equal to this. Right? This is bounded in the whole B1. Belongs to L infinity of B1. And using once again the bonus maximum principle, what I have in fact is that U is continuous, and so this elliptic equation here in the viscosity sense with G in L infinity. Okay. Okay. And now by using this, we can go even further. Under the additional assumption that this set is a subset of omega U, that is omega plus union omega minus, we obtain two additional results. The first one is the non-degeneracy of the free boundary, that is given a point in the interface. There exists a positive C such that the supremum is above this quantity for every R in this interval. And we can prove the negligibility of the free boundary. It means that if the free boundary has less bag measure 0, nothing more. Okay. Now, for any set A, okay, we denote by MdA the smallest possible distance between two parallel hyperplanes containing A. We denote by sigma VU the set where U is 0 in B1, and we define the notion of thickness of the sigma in the R as this quantity, right? The Mg of the is over R. Okay. Now, if we go a little bit further, now if you suppose the thickness is bounded by below by a constant epsilon 0 for our R and every x0 in the interface, then we can prove that U is actually a convex function and that omega is equal to this set. Because that we started by supposing that this is a subset of omega. Okay. And with this, we finally ready to state the classification of global solutions that says that basically if U is a strong solution to this equation, to our equation now in RD, we suppose that again f is elliptic, convex, and homogeneous of degree 1 for equal to 1, 2, and that this set is a subset of omega. If you suppose that this thickness is bounded by below by a constant epsilon r, epsilon 0, and x in the interface, then we can prove that U is a half-space solution. It means that up to a rotation, we can write U in this form here, okay, where C is a constant and gamma belongs to this interval here. It's such that either this equality or this equality holds. This is the main result of this part. And that's it. Thank you very much.